Okay, so you ever stop and think about the invisible stuff happening all around us? Like, why does your hot coffee always go cold? Or why does your ice cold drink get warm on a hot day? Well, you've just stumbled into the world of heat transfer. It's the science that explains how things heat up and cool down. And as we're about to see, understanding its rules is key to, well, engineering pretty much everything.
Right, it's a super basic question, isn't it? We all know it happens, but the science behind it is just fascinating. Everything in the universe is basically on this constant march towards being the same temperature. But what we're going to dig into isn't just that it happens, but how it happens. And maybe more importantly, how fast.
So you can really think of heat transfer as this constant race. Whether we're trying to keep our homes warm in the winter, keep our car engines from overheating, or just keep that coffee hot for a little bit longer, we are constantly fighting to control this invisible flow of energy. And understanding the rules of this race is everything when it comes to designing our world.
Now, first things first, let's get one thing straight. You've probably heard of thermodynamics. That tells us how much energy it takes to do something, like how much heat has to leave your coffee to cool it from 90 degrees down to 80. But heat transfer, that's what we're talking about today, it answers a way more practical question. How long is that going to take? It's all about the rate, the speed of that energy on the move.
For heat to actually move, there's one golden rule. You need a temperature difference. That difference is the engine. It's the driving force. It's kind of like how a voltage difference pushes an electric current through a wire. And it is always a one-way street. Energy flows from hot to cold, always searching for that balance.
You know, our whole idea of what heat even is has a pretty wild history. For the longest time, scientists thought heat was this invisible, weightless fluid called caloric that would literally pour from hot things into cold things. But then guys like Count Rumford started noticing things, like how you could generate endless heat just by rubbing two cannons together. That didn't make sense if heat was a substance. Finally, in the 1840s, James Joule came along and proved it once and for all. Heat isn't a thing at all. It's energy. It's the energy of jiggling molecules.
So if heat is energy in motion, how exactly does it get from point A to point B? Well, it turns out it has a toolkit with three main ways of traveling. And once you understand these three mechanisms, conduction, convection, and radiation, you can start to predict and even control the world around you. First up, we've got conduction. The easiest way to picture this is to think of a metal spoon you left in a hot mug of soup. The heat doesn't just magically jump to your hand, right? It travels. The super energetic soup particles make the spoon's particles start to vibrate like crazy. And that vibration creates a chain reaction that moves molecule by molecule right up the handle to your fingertips. And this very principle here, this is exactly why a thick, puffy winter coat keeps you warmer than a thin jacket. The rule basically is that the thicker something is, the slower heat can move through it. So that extra thickness on your coat is like putting up a bigger wall, slowing down how fast your body heat can escape into the cold air. And of course, the material itself makes a massive difference. Just look at this range. Copper up at the top has this huge conductivity value, which is why a copper pan heats up so incredibly fast. But then look way down at the bottom. Look at air. Air is a terrible conductor. And that's the big secret behind good insulation. Materials like fiberglass insulation aren't special on their own. Their genius is that they're designed to trap millions of tiny pockets of air, using air's terrible conductivity to stop heat in its tracks. Okay, our second tool is convection. This one is all about heat being carried by a moving fluid, like a liquid or a gas. The classic example is a pot of boiling water. The water at the bottom gets hot, it expands, becomes less dense, and floats to the top. Meanwhile, the cooler, denser water at the top sinks down to take its place. This creates this constant rolling current that distributes heat through the whole pot. That circulation is convection in action. And this is exactly why a fan feels so good on a hot day. The fan doesn't actually make the air in the room any colder, right? But what it does is blow that air across your skin, and that moving air dramatically speeds up the rate of convection. It carries heat away from your body much, much faster. It's that enhanced heat transfer that gives you that amazing cooling feeling. Our third and final mechanism is radiation.
And this one's the weird one, because it doesn't need any stuff to travel through. No solids, no liquids, no gases. It's just pure energy, shooting through space as electromagnetic waves. This is it. This is how the incredible warmth of the sun travels through the total vacuum of space to reach us here on Earth.
Now, with radiation, the magic words are to the fourth power. This means the relationship is totally bonkers. It's not linear, it's exponential. As something gets hotter, the amount of heat it radiates just skyrockets. So get this, if you double an object's temperature, it radiates 16 times more energy. 16! That incredible power law is why you can feel the intense, glowing heat from a bonfire, even when you're standing really far away.
But not all surfaces are created equal when it comes to radiation. A shiny surface, like polished aluminum foil, is a really bad radiator. It likes to hold on to its heat. But dark, matte surfaces are the total opposite. They are fantastic at both absorbing and radiating heat. And check this out. Look at human skin. We're almost perfect radiators. This property, it's called emissivity, is exactly why a black car gets so much hotter in the sun than a white one. All right, so now that we have our toolkit, conduction, convection, and radiation, we can start to see how engineers put this knowledge to work, designing things that are incredibly clever at controlling this invisible flow of heat.
Let's put a price tag on this invisible flow. Just think about some plain, uninsulated metal heating ducts running through a cold basement. Heat conducts right through the metal, then it convects into the cool basement air, and it radiates out to all the cold walls. So what's the cost of all that escaping energy? Well, one analysis found it could be over $200 a year, just gone, vanished into thin air. A thermos, or a vacuum flask, is just a brilliant piece of engineering designed to wage war on all three types of heat transfer at once. To stop conduction and convection, there's a vacuum between the inner and outer walls. No air means no medium for heat to move through. To defeat radiation, the inside surfaces are silvered, like a mirror, reflecting thermal energy right back where it came from. And finally, that insulating stopper plugs up the last big escape route at the top. It's a total fortress for your coffee. And this whole energy battle, it's not just happening in your thermos or your house. It is happening inside of you right now. Your own body is a perfect living example of all these heat transfer principles at work.
Okay, I know we've all felt this. The thermostat on the wall says the room is a perfectly comfortable 22 Celsius, 72 Fahrenheit, but you still feel chilly, especially if you're sitting near a big window on a cold winter day. What is going on there?
The answer has less to do with the air and more to do with radiation. Your body is a powerful little radiator, constantly beaming out thermal energy to every single cooler surface around you. And that big cold window in the winter, it's like a thermal magnet, just pulling heat right out of you. So even if the air is warm, your body's losing a ton of heat directly to that cold glass. That net loss of energy is the chill you feel. But while you're losing all that heat, your body is fighting back. It's your own personal furnace. Your metabolism is constantly generating heat, and that rate changes dramatically depending on what you're doing. Look at this. Just getting up and walking more than doubles your heat output compared to just sitting there. Your body is in this constant dynamic battle to balance its energy budget. So where is all of this going? Well, take a look at something like aerogel. People call it frozen smoke. It's more than 90% air, but it's so good at trapping that air in these tiny nanoscale pockets that it actually insulates better than still air all by itself. I mean, that's just mind-bending. This is the cutting edge of stopping heat flow. So, this brings us full circle, back to that race against temperature. Controlling the flow of heat is absolutely fundamental to everything, from our own comfort, to making our buildings energy efficient, to designing next-generation electronics. And now that we can literally engineer materials that can stop heat dead in its tracks, it makes you wonder, what's the next frontier for how we design our world?